We talked a little bit about ice and craters on Mercury, so I don't want to review too much. I just want to go over the sort of slightly more subtle technical things about the 2 to 3 resonance. Now, we haven't talked about Mercury's atmosphere before, and basically it doesn't really have an atmosphere. There are some particles that hang around Mercury because being as close to the sun as it is, and not having a real atmosphere, what happens is that Mercury is blasted by not only solar radiation, but solar particles, because the sun with its very hot atmosphere is constantly sort of evaporating particles off of itself, and they flow out through the planetary system in what we call the solar wind. And what happens is that since Mercury has no atmosphere, the solar wind can impinge directly on Mercury. And these particles hitting Mercury actually can slow down because they bump into Mercury, they can lose some energy. And so what we find is there's sort of a sheath of plasma, we call it, which actually represents particles that are hanging around Mercury for a while, but then they leave. So the reason we don't call this an atmosphere is because it's a constantly changing set of particles. It's not the same particles hanging around for any length of time. You get particles that come in, hit Mercury, lose some energy, and hang around for a while, but then eventually they get re-energized by solar radiation, and they become so hot that they leave again. So you have a kind of a rotating cast of characters in these particles hanging around Mercury. So it's not a true atmosphere. And it's also so thin that by earthly standards, it's really a vacuum anyway. It's not even anything anywhere near the thickness that we would think of as being an atmosphere. And it all, of course, stems from the fact that Mercury has a combination of two things which cause it to not have an atmosphere. One, it's very hot, so all the particles move around with high speeds. And two, Mercury has a low mass. So escape velocity for Mercury is pretty low. Now, so then you have these very hot particles that have thermal velocities that generally are higher than the escape velocity. This is just the classic scenario where you just lose the atmosphere. It just sort of evaporates into space because the particle velocities are higher than the escape velocity. So that's what's happening for Mercury. Now, as we move out and talk about Venus, we'll see that Venus, at its distance, a bit farther out than Mercury is cool enough that it was able to retain a very thick atmosphere. Okay, so final topic about Mercury, not the final thing, but talking about Mercury's magnetic field. We believe that magnetic fields require circulation, electrical circulation of charged particles, because it's just like if you have a coil of wire. If you run electricity, DC electricity, through a closed coil of wire, you generate a magnetic field. So currents generate magnetic fields. But we think that planets have to rotate pretty fast in order to generate the currents. And they also have to have some kind of fluid in there that's electrically conducting. Now, we do see that Mercury has a magnetic field, and this is actually unexpected because it has this very slow spin. Remember, it only spins 3 sidereal days for every 2 years on Mercury. So it's nothing like our good old 24-hour spin on Earth. It's a very slow spin. And so we would expect that that would not drive a kind of dynamo, like the one that's running inside Earth's core right now, generating Earth's magnetic field. We just don't see how we can have vigorous enough motions with this very slow spin. So the fact that there is a magnetic field is that actually does not fit the paradigm. We don't really understand that very well, and that's one of the things that Mercury Messenger is going to be helping us to understand. And that is actually a relevant topic, even if we think about life on other planets, because we think that magnetic fields are very important for protecting life because they form magnetospheres that tend to shield creatures and evolving cells from things like cosmic rays that can be very harmful to genetic material. So you want to have magnetic fields on a planet where you're thinking life might be. And so we'd like to understand as much as we can about how magnetic fields form. So that's one of the reasons why Mercury is of interest to us in that respect. All right, so when we look at the moon and Mercury, of course, we see lots and lots of craters. They're both very gray-looking, and they're both very heavily cratered surfaces. So, of course, they're caused by impacts. Actually, in the case of Mercury and the moon, we don't really see much in the way of volcanic cratering. It's to a large extent caused by impacts. And this also leads to erosion on both Mercury and the moon, since there's no liquid water or air. All right, so we haven't talked about the actual process of formation of craters, but what happens is it's pretty simple and straightforward and intuitive. It's basically a big blob. It's sort of like kind of like the Thor method of producing a big hole. Anybody's ever heard of Thor? The dude with the big mallet, crochet thing, the hammer, the big hammer. Right. Actually, I think in this movie I predict there's going to be a line in there. But Thor says, or no, somebody else, maybe not Thor, maybe like Captain America, or, I don't know, maybe Iron Man, might appear and say, we're going to need a bigger hammer. I just like that because I'm into Jaws. You know, we're going to need a bigger boat, the alligator chasing her around. We're going to need a bigger hammer. Just check that. It hasn't come out yet, so I couldn't know. This is just a prediction, right? I don't have any special knowledge. Anyway, okay, so here comes the big hammer in the form of a meteorite, which is actually moving at several thousand kilometers per second. So this is an incredible impact that we're talking about. Incredible amount of kinetic energy is in a meteorite when it strikes. And this, of course, you know, we could be speaking of Mercury or the Moon or even the Earth. Very, very large, thousands of kilometers per second type velocities. So what happens is it completely pulverizes material on the surface, creates shock waves which go down through, just like the Chloris Basin was like a mega impact where the shock waves actually went completely through the planet and formed geological features on the other side. That's unusual. But a typical impact does produce shock waves which actually can melt layers of these substrata. And then we have ejecta that comes out, and that can be glassy. And we see this on Earth. We see glassy ejecta around even volcanic craters, actually, on Earth, as well as impact craters. Okay, so impact craters can form, of course, at any time, and this is just a depiction. We have the kinetic energy leading to melting of a lot of the material, and the molten material can get ejected and form the glassy ejecta. So we have a typical flat surface inside, surrounded by a raised rim, and then another blanket of ejected material out there. And so this is these are some glassy ejecta examples that were brought back from the moon by the Apollo astronauts. And the reason that we're looking at this is because these globules that were formed in a huge impact, material melted, flew through, well, it didn't fly through any air, this is the moon we're talking about. It just flew along, but it cooled off and solidified. But if you look at these things under a microscope, what you find is that the glassy ejecta itself actually has micro craters on it. And these are things we never see on Earth because these microcraters are actually due to thousands of kilometer per second impacts by dust, little dust particles that actually are walloping glassy ejecta while flying and running some distance on the moon. And so even the dust particles can create microcraters. We never see this on Earth because dust like that never gets through Earth's atmosphere. It just forms shooting stars on Earth, right? Burns up and forms bright streaks. But it makes it to the surface on the moon and can form this type of feature. Alrighty, so, well, okay. There's something we think of as the rate of production of craters. We've actually touched on this a little bit already because when we talked about the moon, we noted that there's a lot less cratering on the Maria than there are on the Highlands, right? But then it turned out that the Maria are almost as old as the Highlands. So what that means is that about 3 billion years ago or so, the rate at which stuff was bombarding the moon dropped precipitously because even though the Maria are only a little younger than the Highlands, they have a lot less craters. So there's just a lot less stuff, for some reason, that was actually available to hit. So we have this idea of the rate of production of craters due to impacts. So we see that that rate dropped around 3 billion years ago, but we can even parse it a little more carefully and think about the size of the chunks that we're talking about. And it turns out that small craters are produced a lot more frequently than large craters. And frankly, if that weren't true, we probably wouldn't be here right now because that would mean if it was the opposite, there'd be a lot of huge impacts and then we'd be going through, you know, dinosaur extinction types of events every few years and consequently, you know, probably wouldn't be having this conversation right now. So 10-kilometer craters only form around once every 10 million years or so, as it says here. And then subsequent erosion can fill in smaller craters. All right, so when we're talking about this thousands of kilometers per second type of impact velocity, we're talking about, well, the impact velocity, okay? It has to do with the mass of the planet and the radius of the planet. And you can see just qualitatively what's going on here is we've already talked about this because we talked about how there's this idea of the escape velocity, and this was connected with the idea of the atmosphere escaping, right? If you have a planet with a large mass, it's going to have a larger escape velocity. So a given gas is not going to escape as readily at a given temperature. It's not going to escape as readily from a massive planet as from a lower mass planet, because a massive planet has a higher bar, it has a higher escape velocity. So at the same temperature, the lower mass planet is actually going to lose more of the atmosphere than a higher mass planet. The higher mass planet just has a strong gravitational attraction. Well, if we run the movie in reverse and we think about, instead of escaping, we think about dropping something from a large distance, then the impact velocity that the object actually strikes with is just equal to the escape velocity. It's just like you're running the movie in reverse. And so we can actually compute the escape velocities. And so, I guess I should have said thousands of kilometers. A few kilometers per second, but that's thousands of kilometers per hour. A few kilometers per second is still mighty, mighty fast. And if we look at, for example, the Earth, it's 11 kilometers per second. So again, if you have like a large asteroid, a mile across, let's say, and it's moving at 11 kilometers per second, I mean, you can grasp that's going to be a huge amount of kinetic energy. In fact, it's going to be probably like 1,000 megaton nuclear bomb equivalent. So the impact velocity is lower on Mercury and the Moon. It's about half as much on the Moon as it is on Mercury. You see the 2.4 kilometers per second for Moon impact and 4.3 kilometers per second for Mercury. So the impacts are more violent on Mercury than they are on the Moon. That's for sure. And yet what we find is something that's a little bit surprising. Even though the impacts are more violent on Mercury than they are on the Moon, because this Mercury having a higher mass has this higher impact velocity, so the actual speeds are about twice as high. And you remember that the kinetic energy goes as 1/2 mass times the square of the velocity. So if we drop the same asteroid on Mercury and the Moon, you're going to have about 4 times as much kinetic energy, because it goes like the square of the velocity. And yet when we look at Mercury and the Moon, we actually find that the craters are smaller on Mercury than they are on the Moon. So you would think, just based on the violence of the impact alone, that the craters would be larger on Mercury because it's a more violent impact, right? Dropping the same asteroid on Mercury and the Moon, and it hits harder on Mercury, why would you have a larger crater? It's a bigger bang after all. But what's actually happening here is there's another effect of gravity that we haven't thought about yet. There's 2 effects that gravity has on the size of craters. One is that we do have a more violent impact on Mercury than we do on the Moon. But the secondary effect is that as the ejecta flies out of the crater, it's then subject to gravitational attraction, which of course pulls it back down to the ground, right? And on Mercury, the stronger gravitational attraction for a given explosion will actually cause the ejecta to come down faster. So they're competing effects, actually. On Mercury, you have a larger explosion initially, but you also have stronger gravity that pulls the ejecta down. And it turns out the second effect actually wins out. So we have more compact craters on Mercury than on the Moon because of the fact that the effect of gravity on the ejecta tends to bring them down closer to the center of the crater.